Hello friends, guess where I am today? I'm at the UL lab in Melville, New York, which is just outside of New York City, and today we're going to learn some really cool things about how electronics and electricity and power is tested here at the Melville lab. So come on, let's go check it out. Okay friends, so I'm here in Melville at the Power Distribution Lab, and I'm here with Ed. Say hi, Ed.
But I'm Ed, you're not Ed.
Yeah,
oh, hi Ed.
Oh, Ed, so tell me, how long have you been here at UL?
I've been here quite a while.
How long?
I've been here, well, let's put it this way. When the Lord said, let there be light, who do you think did the investigation?
Okay.
When Ben Franklin and I were inventing the lightning rod and running a kite up with a key,
Yeah.
we figured out that cloud-to-cloud lightning strikes could put a big impulse on the power lines, come on down, and give you a problem with your computer or your Xbox. Of course, we didn't have an Xbox back then,
right,
but
right.
that's okay. And you have your power strips that usually help you protect from those power surges.
Okay. Great.
And the little device that's inside that is a small device called an MOV, or a metal oxide varistor. This little guy is going to give you the protection that you want to keep the insulation system in a good, safe condition and prevent fires.
Okay, great. Now, why is this testing and everything that you do here, why is it so important?
This is designed to come and allow us to evaluate the products so that the MOV, the device,
Of course.
can be matched to the proper application.
Okay.
If it's not, this test will demonstrate what could happen.
Great, okay. Is it all right if we run the test?
Sure,
All
let's
right.
go ahead.
All right, perfect.
Right now, we have a surge generator that's going to bring a surge on the power line and go right to that component, and we're going to cover it with cheesecloth to demonstrate any fire. Right now we're applying an impulse of about 6,000 volts, 3,000 amperes to this product to see how it reacts.
Okay. Ooh. Wow, okay. Now, why did it do that?
Okay, the energy contained within the impulse was more than what this was designed for. They normally would not react like this. Now you know the limitations of this particular product.
Wow, okay. Wow. It's all for safety. Perfect. Well, thank you very much, Ed.
Oh, you're welcome.
So I'm now here in the core electrical lab, and I'm here with John. Say hi, John.
This is how you learn.
No, John, that's my line.
Oh, sorry.
Just
Dennis.
say hi, John.
Hi, John.
No. So John, tell me, what do you do here at UL?
I test appliances, appliance controls. Controls are the things that are inside the appliance, like the guts of the appliance that make the appliance work.
Wow, okay, great. Now, why is that testing so important?
It's important because the appliances can have things happen to them that might make them unsafe, and the control is supposed to protect the appliance, but also protect your house.
Okay.
It's supposed to protect your house from something that could heat up and catch fire, or something that could shock you, that if you touch the outside of the appliance, it could shock you. So we want to make sure that the designers of the appliances make them safe from shock and fire hazards.
Okay, wow, perfect. Now, what kind of test setup do you have here?
Well, I'm testing a component today, a switch that comes from an appliance.
Okay.
And we're using a robot arm to move the switch back and forth. The switch gets mounted in a vise, and then I use the robot to turn it on and off. And in order to make the robot work, I have to type in computer code. It's sort of like learning a new language.
Really?
It's not exactly English. It looks like English, but I had to study it from the robot manual before I was able to make it work.
Okay.
The reason why we're flipping the switch on and off is it's called an endurance test. The appliance, you can imagine throughout the course of the life of the appliance, it's going to get turned on and off many, many times. So we want to make sure the switch can survive the life cycle of that appliance. So in this case, it could be running for 30,000 times or for 100,000 times.
Wow. So John, why do you use these kinds of light bulbs that we see here?
Actually, Dennis, today I didn't have to use these light bulbs, but I chose them as a tribute to UL because they're old. They look kind of old-timey light bulbs, and UL has actually been testing products for over 120 years. So I wanted to choose something that's sort of a tribute to that, and it's kind of to show a balance of how we have been testing products for over 120 years, but we also are testing the latest technology today.
This is excellent. John, thank you so much for your time and for explaining all of this to us.
You're welcome, Dennis.
Okay, so I'm in another section of the power distribution lab, and I'm here with Jim. Say hi, Jim.
Hi, Jim.
Why do you always go? I don't understand. So Jim, what do we have here? What is this setup?
This is a test demonstration of how a circuit breaker works and how it's supposed to protect the wires in your walls from overheating and starting a fire.
What do you do here specifically at UL?
Well, I test circuit breakers, electric vehicle chargers, ground fault circuit interrupters, switches, relays, anything that has to do with high power, turning stuff on and off to make sure that it works safely, that you don't have a fire or a shock hazard.
Okay, now why is this testing so important?
Because people are under a misunderstanding what circuit breakers do. A lot of times they think they're people protection, and they're actually protection for wires in your walls. And if they're not used properly or set up properly, you can start a fire in your house.
Oh, really? So if I were to grab a fork and put it in the socket, this won't protect me?
No, it won't.
Why is that?
Because it's not a GFCI circuit breaker.
Oh, okay.
This is made for overcurrent protection.
Okay.
It has 2 bimetals in them, and when the bimetals get hot, they open up, which causes the circuit breaker to turn off, just like that.
Okay. But it's mainly to protect this wire here.
Correct.
Okay, and if this wire gets too hot?
It'll start the insulation in your house on fire.
Okay.
Here we have common household wire creating a short circuit on a 20 amp circuit breaker. We have 5,000 amps at 240 volts going through this breaker. When we start the test, the breaker should trip and the wire should stay intact. The cotton should not go on fire, and that will show that the product did its job.
Woo!
And you see, we had a failure. What we had here, the circuit breaker worked, the wire turned off, but the arc chutes were a little too big, so the spark went too far, which set the cotton on fire.
Okay.
So that would be considered a failure. This is a 7.5-inch piece of standard copper 12 gauge wire that you would find in your home. And what we're doing is we're creating a dead short circuit across the 5,000 amps, 240 volt circuit.
It's loud. Oh, man.
Okay.
Wow.
Now, you see power electricity, and you see why circuit breakers and fuses are necessary. All that's left of that copper wire is just the sleeving.
Wow. Okay. So we had an excellent day today here at the UL lab in Melville, New York, where we learned so much about power and electricity and some of the tests that are done on products that we use every single day. It's not only very important for us to test these things, but as you can see, it was a whole lot of fun. For UL Safety Smart, I'm Dennis Avalar, and that's how you learn.